Hi, in this video we're going to be discussing the mechanisms and the reactions occurring in the TCA cycle, the citric acid cycle, or the Krebs cycle. They're all synonyms, okay? This is going to be taking place in the mitochondria of the cell, okay? We are going to start off after pyruvate has been turned into acetyl-CoA using the PDC complex. Maybe I'll make a video about that, but right now, we're going to be talking about the acetyl-CoA. All right. Now, with the acetyl-CoA, we're going to add it onto an oxaloacetate to have a condensation reaction. What that means is we're going to condense them together to form what's called a citrate. Okay. Now, we are synthesizing, we are synthesizing a citrate. So the enzyme is going to be called citrate synthetase. Okay. Now that we have citrate synthetase, and that's going to be the first reaction, and that type of reaction is a condensation reaction. The second reaction is transforming citrate into an isocitrate. Alright, now come on, we are changing it to another form of citrate, going from citrate into isocitrate. So what enzyme do you think we're using? You're right, a aconitase. Out of nowhere. No, it's not an isomerase. It's going to be a unique enzyme called a aconitase. Why? Because of the intermediate to get to isocitrate. Alright? We are actually going to dehydrate the citrate and take out an OH in the form of water. And we're going to turn it into cis-aconitase, and then we're actually going to add water back into it immediately. So it's a dehydration, rehydration following each other. Okay. So we're going to rehydrate that aconitase, and that's going to turn it into or isocitrate. That's going to turn into isocitrate. And that's the second step. All right. So there's a 2A and a 2B, a dehydration followed by a rehydration, or just a hydration reaction. All right. So now we have isocitrate. Okay, now's when we're going to have energy payoff. Okay, we're going to, from here on out, we are going to pretty much be gaining energy either in the form of electron acceptors or a GTP. Okay, we're not making any ATP here. It's going to be a GTP this time. All right, but anyway, we're going to have the isocitrate reduce an NAD+, okay? So we're going to have the isocitrate, we're going to dehydrogenate it, okay? So we are going to use isocitrate dehydrogenase, okay? What the name doesn't imply, though, is that we're also having we are removing a carboxyl group. So this reaction is actually going to be an oxidative decarboxylation. Not only are we reducing not only are we getting rid of NADHs, but we're also getting rid of a CO2. This process is actually going to create what's called an alpha-ketoglutarate. If that sounds familiar, it should, because we actually use alpha-ketoglutarate to create glutamates. Okay, but those are covered in another video. We're focused on the TCA cycle. So with alpha-ketoglutarate, we're going to go through the same process again, where we are going to reduce NADHs, or we're going to reduce an NAD molecule. We're also going to kick off a CO2, so this is going to be an oxidative decarboxylation. The name of this enzyme is going to be alpha-ketoglutarate dehydrogenase. Okay. What's unique about this one is the fact that we're actually having a coenzyme A come into it and adding itself on to that alpha-ketoglutarate. This product is going to be succinyl-CoA. Okay? So once again, we went from alpha-ketoglutarate, we added in a coenzyme A to create succinyl-CoA. Now that we have succinyl-CoA, we're going to want to change it into a succinate. However, where this the enzyme gets its name, the enzyme for this reaction gets its name, is going to be from the fact that we are phosphorylating a GDP. Alright, so the name of this reaction is going to be called succinate thiokinase, because we're going to be using that coenzyme A to have a substrate level phosphorylation reaction occurring while we create that succinate. Okay, so we're trying to be as efficient as possible with these reactions to create energy. So we're going to have succinyl CoA. We're going to kick off that CoA, and we're going to produce a GTP. Now that we have succinate, we're going to dehydrogenate it again, or dehydrogenate the succinate. This is going to create fumarate. And since we're taking off hydrogen atoms, we're going to be reducing an electron carrier. This time, instead of using NAD pluses, we're going to be using FAD. So we're going to actually be using succinate dehydrogenase to reduce FAD into FADH2 to create fumarate. One of the ways that I remember this is that this is the first time that we see fumarate. So fumarate, FAD. Everything else is going to be NAD+. All right. Since we have fumarate, it's going to be very, very similar to the next substrate or the next ingredient of this TCA cycle, and that's going to be malate. So we're going to go from fumarate to malate. In order to do so, we're going to use the enzyme called fumarase. Okay. This reaction is going to be a hydration again, where we're adding a water into fumarate and to break apart a double bond between the two C's, okay, to create malate. Now that we have malate, we're going to use malate dehydrogenase to create what? Right, oxaloacetate. So we're going back to the beginning with this malate dehydrogenase. If that sounds familiar, it should, because that enzyme was actually one of the ways that we got oxaloacetate out of the mitochondria. But you can check out one of those videos if you so choose. So that's pretty much the Krebs cycle. The next topic that we're going to cover is going to be the electron transport chain that's linked very closely with this Krebs cycle. We're going to take all those electron carriers, those FADH2s, those NADHs, and we're actually going to put them through an electron transport chain to pass on electrons and as well as create an energy gradient. But more on that in the next video.